In Episode 4, we utilized principles of space-time engineering to establish the spectral limits of the quantum vacuum. In this episode, we're going to test our equations. If our construct is physically valid, then we should be able to make experimental predictions with extreme precision. Two scales of reality exist. That is, the fundamental particle scale and the cosmological scale. In this episode, we're going to focus on the fundamental particle scale of reality. Specifically, we're going to use our quantum vacuum frequency equations to precisely calculate the size of the proton and neutron. Both of these particles are termed composites, because they are said to contain even more fundamental particles, quarks. For now, in this episode, we shall disregard their quark substructure and consider them as singular entities. One of the primary questions we must address is size. What exactly does size mean? Well, believe it or not, the answer to this question, to some degree, depends upon whom you ask. The public relations answer appears in this illustration, but more complicated answers exist involving wave functions and probability distributions. However, in this episode, we're asking the question: does the quantum vacuum play a role in determining the size of fundamental particles? Or more specifically we ask, is the size of a composite fundamental particle dependent upon an equilibrium condition between the particle itself and the polarized zero-point field surrounding it? Let's find out. Let's begin with some basic observations. Firstly, in nature, we see that all systems seek to achieve the lowest possible energy state. Secondly, in the case of fundamental particles, its mass-energy density is significantly higher than the energy density at a radial point from the particle, at infinity. So, what prevents a fundamental particle from diffusing itself into non-existence due to the energy gradient between its center and radial infinity? Perhaps the answer to this question is that its mass-energy density is in equilibrium with its spectral energy density. If so, the equilibrium point between these two forms of energy may represent a boundary. A boundary that we can interpret as size. This now becomes an hypothesis we can test. Assuming that a radius value exists equilibrating mass-energy density with spectral energy density, we shall denote it as the zero-point field equilibrium radius. To universally address all fundamental particles, we shall ignore the internal structure and forces associated with all composite particles. Therefore, we hypothesize that the value of zero-point field equilibrium radius coincides with the root mean squared charge radius of the proton and the mean squared charge radius of the neutron. Let's now look at how we can test our hypothesis. Before we can test our hypothesis, we'll lay out the tools we need. We'll classify them as preconditions, which include the speed of light, Planck's constant, proton mass, neutron mass, particle radii and the Compton frequency of the proton and neutron. Importantly, it should be noted that the proton root mean squared charge radius is taken from the National Institute of Standards and Technology 2022 database, and the neutron mean squared charge radius is a guesstimate value required to initialize the computational solution algorithm utilized to test our hypothesis. With our preconditions in place, we are ready to define our computational solution algorithm. However, before we can define an algorithm, we must mathematically interpret the hypothesis to be tested. In this case, we propose that the ratio of harmonic cutoff frequency to Compton frequency equals the ratio of particle mass to electron mass. Recalling Episode 4, we know that the harmonic cutoff frequency represents the upper frequency limit of the quantum vacuum, at position r, induced by mass m. Hence, we are suggesting that the ratio of quantum vacuum upper frequency limit to Compton frequency is equal to the ratio of particle mass to electron mass. Therefore, due to the massive similarity between the proton and neutron, and the mass of the electron acting as a third relative measure, we should, in principle, be able to find two zero-point field equilibrium radius solutions, constrained by particle Compton frequencies and masses. Once the computational solution algorithm has been executed, we obtain the results and instantly see that they are exceptionally impressive. The results obtained match physical measurements so precisely, that in addition to our hypothesis being experimentally validated, The existence of the harmonic cutoff frequency has also been experimentally confirmed by implication. Let's now compare our results to authoritative sources. The first set of comparisons to authoritative sources we shall make involves two of them. That is, the SELEX collaboration measurement of the proton root mean squared charge radius in 2001, and the neutron mean squared charge radius measured in 1995 by Kopetsky and utilized in 2002 by Karmanov. The reason the Karmanov value is utilized is because of the revised experimental tolerance, compared to the original 1995 Kopetsky research. The Karmanov conclusion is slightly more uncertain, making it a marginally better baseline to utilize as an authoritative comparison. Very importantly, an extract taken from Sparveris describes how the neutron mean squared charge radius manifests as a negative quantity. Sparveris writes that, quote, "The neutron is a cornerstone in our depiction of the visible universe. Despite the neutron's zero net electric charge, the asymmetric distribution of the positively and negatively charged quarks, a result of the complex quark-gluon dynamics, lead to a negative value for its squared charge radius." End quote. Hence, this negative radius concept should remain in the front of your mind as we move forward. First up, let's compare our zero-point field equilibrium radius for the proton to its root mean squared charge radius as physically measured by the SELEX collaboration. As we can see, the correlation to experimental observation is astonishing. Thus, we have experimentally validated our hypothesis with respect to the proton. Next, let's compare our hypothesis to the mean squared charge radius of the neutron. Once again, we see an astonishing correlation of our zero-point field equilibrium radius to experimental observation. Thus, we have experimentally validated our hypothesis with respect to the neutron. But that's not all. We have also demonstrated how we have overcome the standard model of particle physics limitation of negative radius, as discussed by Sparveris. This is not a trivial achievement and should not be flippantly dismissed. It demonstrates how the concept of zero-point field equilibrium radius compensates for an inconvenient limitation in the standard model of particle physics. The experimental observations we are referencing are decades old. Let's now look at something a little more recent. Our next set of comparisons to authoritative sources involves Sparveris and the particle data group. For this slide, we'll focus on the neutron, not the proton. A significant quantity of root mean squared charge radius values for the proton exist in the literature, so there's no need to reference them here. There can be no doubt that our zero-point field equilibrium radius for the proton is experimentally confirmed beyond question. However, since the mean squared charge radius of the neutron is a negative quantity according to the standard model of particle physics, we should gather more experimental evidence in order to emphasize our hypothesis. Sparveris proposes a solution for mean squared charge radius, and criticizes so-called particle data group discrepancies. But, when we convert mean squared charge radii to the natural form of zero-point field equilibrium radius, we find that the Sparveris solution, inclusive of tolerance declarations, provides a marginal improvement over the first particle data group discrepancy referenced. So in fact, not much significantly new information can be derived from the Sparveris solution. However, the overlap between the solutions boxed in red indicates that the zero-point field equilibrium radius hypothesis has been validated for the second instance based upon published experimental observations. Next, we'll develop analytical solutions for the zero-point field equilibrium radius of the proton and neutron. The first step in establishing analytical solutions for the zero-point field equilibrium radius of the proton and neutron requires the simplification of the harmonic cutoff function. To achieve this, we commence by recognizing that at the fundamental particle scale of reality, the refractive index evaluates to unity. This is mathematically demonstrated by evaluating the refractive index utilizing our numerical solutions for zero-point field equilibrium radius. Similarly, we execute an evaluation of the harmonic cutoff function to determine a reference solution. Next, we investigate the numerical contribution of key terms within the harmonic cutoff function in the same manner as previously. In doing so, we're able to establish a simplified form of the ratio of energy densities. Moreover, we're also able to determine that the key terms within the harmonic cutoff function are equal, as shown. Once this equality has been recognized, it is a very simple process to generate and evaluate a simplified harmonic cutoff function. As you can see, the simplified form generates an almost identical result to the reference solution, with trivial error. With the simplified harmonic cutoff function in place, we may now simplify the harmonic cutoff mode and frequency. So, let's move on. Simplifying the harmonic cutoff mode and frequency is a very easy process once the simplified harmonic cutoff function has been generated. Utilizing a similar substitution process as before, we're able to generate the simplified harmonic cutoff mode and frequency as shown. We can further simplify the frequency expression by recognizing a collected group of terms form a physical constant, as identified. Subsequently, the second simplified harmonic cutoff frequency is generated and shown to be 100% similar to the original solution. With the harmonic cutoff function, mode and frequency simplified, we are now in a position to derive exact analytical expressions for the zero-point field equilibrium radius of the proton and neutron. The derivation sequence for the zero-point field equilibrium radius of the proton and neutron is astonishingly simple once the significance of Compton frequencies is realized. When we evaluate the ratio of particle Compton frequency squared to the electron Compton frequency, we find that they're equal to the second simplified harmonic cutoff frequency, as shown. Once this relationship has been realized, a string of simple substitutions yields the exact analytical solution for the zero-point field equilibrium radius of the proton and neutron. These exact analytical solutions may seem innocuous, but nothing could be farther from the truth. The fact that the form of each solution is identical is extremely important and very telling. Given that we have established the experimental validity of both solutions, it is a very powerful statement that they have the same form. This is exactly what we would expect if we were discovering these particles for the first time, due to the similarity of their masses. The standard model of particle physics does not, and cannot, achieve this. When utilizing conventional methods, the neutron mean squared charge radius is a negative quantity, whilst the root mean squared charge radius of the proton is a positive quantity. This disparity is a significant indicator of a problem within the standard model of particle physics, requiring correction. We know for a fact that a problem exists because we have derived a solution without the same disparity. In the next slide, we'll develop a graphical representation of the zero-point field equilibrium radius of the neutron, which is also, as we have shown, the mean squared charge radius. So, let's get going. In this slide, we see 4 computer-generated graphical outputs. That is, the charge density and its first 3 derivatives. By necessity, the y-axis has been multi-scaled to accommodate all graphs. We have also included the classical electron radius to emphasize relative x scales. Computationally, we have been able to determine that the zero-point field equilibrium radius is approximately 78% of the distance to the minimum charge density radius. Similarly, we compute that the zero-point field equilibrium radius is approximately 29% of the value of classical electron radius, whilst the minimum charge density radius is approximately 38% of that value. Let's now have a detailed look at each one of these graphs. Here is a higher resolution view of the neutron charge density, with points of significance circled. It should be noted that this charge distribution, which has been derived utilizing the electrogravity-magnetic construct, was experimentally verified by Juzo Zenihiro from Kyoto University in 2011. As part of his doctoral dissertation, the experiment was performed at the ring cyclotron facility in the Research Center for Nuclear Physics at Osaka University. Similarly, here is a higher resolution view of the first derivative of charge density, with points of significance circled. The second derivative of charge density is a little more interesting, with an additional couple of points of significance. Lastly, with a third derivative of charge density, we have more closely inspected the family of curves presented on the initial slide. Next, we're going to investigate the electric and magnetic radii associated with the proton and neutron. In 2004, Hammer and Meissner executed a theoretical investigation in order to decompose specific properties of the proton and neutron, termed electromagnetic form factors. They establish an estimate for the neutron magnetic radius, proton magnetic radius and proton electric radius. Similarly, in the following year, Storti also derived estimates for these properties, as shown. The Storti estimate for proton electric radius matches the Hammer and Meissner estimate precisely, but disagrees with the Hammer and Meissner estimates of proton and neutron magnetic radius. Hence, the disparity between the Hammer and Meissner results, and the Storti results, requires explanation. In addition to this, the National Institute of Standards and Technology adds another layer of complexity by publishing the root mean squared charge radius of the proton to be in conflict with the result experimentally determined by the SELEX collaboration. So, our objective now is to join the dots and chant a consistent story. We have concluded that the disparity between results may be reconciled by 4 points. Firstly, the National Institute of Standards and Technology, root mean squared charge radius for the proton, and our proton electric radius, are the same measurement. Secondly, the SELEX collaboration, root mean squared charge radius, and our zero-point field equilibrium radius, are the same measurement. Thirdly, the proton magnetic radius coincides with the neutron magnetic radius. And lastly, the neutron magnetic radius coincides with the zero-point field equilibrium radius. Let's now summarize everything we have covered in this presentation. The fundamental concept presented herein is the principle of zero-point field equilibrium. The simplest description of this principle being the balance of forces between expansion and compression. A fundamental particle experiences a natural tendency to expand and diffuse itself into non-existence, because it has a higher energy state than the quantum vacuum at infinity. However, the quantum vacuum pushes back on the fundamental particle, which acts to contain it, and the forces balance at the zero-point field equilibrium radius. In the case of composite particles, such as the proton and neutron, the resistance provided by the quantum vacuum is less dominant because of the complex internal structure. As combinations of particles produce ever larger physical structures, the resistance provided by the quantum vacuum diminishes significantly, as structural atomic and molecular bonds dominate. The zero-point field equilibrium radius refers to the radial distance from the center of mass of an object, to the point where its mass-energy density equals the sum of the quantum vacuum spectral energy density, contained in the space-time manifold surrounding it. For example, in the case of the Earth, the zero-point field equilibrium radius occurs at its surface. That is, at the point where matter stops. In the case of composite particles, that is, the proton and neutron, the zero-point field equilibrium radius occurs at locations which do not have a solid surface. Instead, they possess other features which coincide with this zero-point field equilibrium radius value. This phenomenon occurs because the presence of mass-energy polarizes the quantum vacuum into what is termed the polarizable vacuum. The ground state of the quantum vacuum is termed the zero-point field. This is the minimum permissible energy state of the quantum vacuum. In this condition, the quantum vacuum comprises of an infinitely broad spectrum of potential frequencies. That is, from 0 Hz to infinity. However, the presence of mass energy modifies the quantum vacuum spectral bandwidth. It upshifts the lower spectral limit and downshifts the upper spectral limit. In other words, it compresses the bandwidth of the quantum vacuum. This means that the probability of virtual photons popping into existence outside these local frequency limits is 0. Hence, virtual photons can only experience the creation and annihilation operation between the local spectral limits constrained by the polarizable vacuum. We will review these frequency constraints on the next slide. The lower spectral limit of the quantum vacuum is termed the fundamental frequency. It differs for all particles due to their varying masses. The ground state of the quantum vacuum is termed the zero-point field. In the presence of matter energy, the quantum vacuum is modified away from its ground state. This kind of quantum vacuum modification yields a polarized vacuum. The polarized vacuum causes the lower frequency limit of the quantum vacuum ground state, that is, the zero-point field, to be upshifted from 0 Hz to approximately 36 GHz, as shown. This means that no permissible quantum vacuum frequencies exist at location R, beneath approximately 36 GHz. In other words, the quantum vacuum spectrum of frequencies commences at 36 GHz, for that specific particle, at that specific location. The presence of matter energy also induces an effect on the upper spectral limit of the quantum vacuum. In fact, it downshifts the zero-point field limit from infinity to the values shown. These are termed harmonic cutoff frequencies, which are particle and location specific, as indicated. Hence, quantum vacuum frequencies above these boundaries do not exist. This means that the presence of matter energy transforms the broadband zero-point field frequency spectrum into a narrow-band polarizable vacuum frequency spectrum. This is an extremely important concept to grasp and retain. So please, etch this deeply into your mind. In addition, it should not have escaped your attention that the harmonic cutoff frequencies of these particles may be expressed very precisely in terms of their respective Compton frequencies, as indicated. This is quite an encouraging sign, so please note it down. By the way, in case it has escaped your attention, the transformation of the zero-point field into a polarizable vacuum solves the infinite energy and the vanishing volume problem associated with quantum electrodynamics. Since no point in space-time is ever truly devoid of superimposed energy, the quantum vacuum can never be in its ground state, and therefore, its upper frequency limit can never actually be infinity. Hence, the potential for the universe to collapse in upon itself vanishes and the dilemma is resolved. From these frequency relationships, we were able to derive exact analytical solutions for the root mean squared charge radius of the proton, the mean squared charge radius of the neutron, and the minimum charge density radius of the neutron. The significance of this being that our radii derivations have been experimentally verified to extremely high precision. Moreover, the electrogravity-magnetic construct solves the standard model of particle physics problem of a negative quantity being associated with neutron radius. The fact that the standard model of particle physics does not, and cannot, express the mean squared charge radius of the neutron as a simple positive length measurement, is indicative of an incomplete method. Utilizing our zero-point field equilibrium radii, we numerically determined the proton electric radius, the proton magnetic radius and the neutron magnetic radius. Whereby, our solution predicts the two magnetic radii to be equal. However, at our present level of technology, the neutron mean squared charge radius, proton magnetic radius and neutron magnetic radius are experimentally indistinguishable from each other. The final hurdle we have overcome is the significant difference between the value of root mean squared charge radius adopted by the National Institute of Standards and Technology, and the value experimentally measured by large colliders, as utilized by the CELEX collaboration. We propose that the National Institute of Standards and Technology have misidentified their 2022 value of proton root mean squared charge radius. That is, it actually represents the proton electric radius. For viewers wishing to investigate our mathematical derivation processes, please feel free to refer to any of the links shown.